Okay, so start from this week, we are talking about, we are going to discuss diffusion model. So diffusion model is one of the primary method that for generating stuffs like images, video, or even like audio or text. Like the GPT-based large language model is one of the two major approach in the generative AI。所以今天我们会开始来介绍 diffusion 的模型。那 diffusion 的模型是目前两种主流的生成式 AI 的方法。那先简单的示范一下它的样子。So let's begin with a simple illustration demo of what it is. So I'm using a Hugging Face space. In general, one of the most popular methods to use diffusion model to generate image or video is using Comfy UI, which is Comfy UI. It has online services, and also you can run this software on your local machine, which is quite easy. You can even run it on the Windows, because it already has been already packed in several convenient package that you can install quite easily to try out many different algorithm or models in different workflows that it has been built by the community. But right now, currently, I'm trying to use Hugging Face space to try a few models. For it, this one is I'm using Flux. Flux has been here for a while. But I'm just trying to show you a little bit about how to what it is. I'm not trying to showcase the most capable or most amazing ability of a diffusion model. I'm just showcasing, try to illustrate what it is, just in case you are not familiar with what it is, so that we can on the same page. So for example, this is an image that I just generated by using a prompt. So I give a prompt here. A prompt is usually in this context is a sentence, maybe in a more detailed way or maybe not, but it is a sentence, and I use this prompt to guide the model to actually generate an image. So in here, I'm generating a park in the winter. I can change this one from winter to in the summer. Okay. So it become a park in the summer. Maybe I can change a bird view of a park. And so I change it up perspective, and from maybe I can change it to a drone view. Like I'm looking at this park from a drone. So I can change a lot. You can see it's quite fast. Typically, I mean, originally, it a signature of what the diffusion model is. It's kind of slow because it iterate for a lot of different for a long step. But Flux is quite. I mean, modern diffusion model can generate in like a few steps instead of like 1,000 steps, like 30, 50, 100, or 1,000 steps. Instead, you only use like 4 steps to generate. So you can see that the generating process is quite fast and almost unnoticeable. there's a lot of different parameters that you can adjust and tweak and play with. There's also like other Hugging Face space. There are some examples that you may try to give you if you don't have an idea of what you want to generate, you can try some presetted things, so that you can have some idea of inspiration of what you can actually achieve. Um, a typical image that had been used a lot in diffusion papers or technology is an astronaut. I don't know how to spell it. Let me spell it a little bit. Okay. Astronaut riding a horse on the moon on Mars. Okay, on Mars is quite okay. The reason that people choose this prompt to show this image is because this, I mean, like 4 or 5 years ago, before diffusion model has been developed, you can pretty sure that there's no real image or no similar image about an astronaut riding a horse on a moon or on Mars. You can pretty sure you have never seen things like before. So this prompt is serving as a purpose of demonstrating that this diffusion model has certain creativity that can combine several noun, like astronaut. We know what the astronaut. We know what horse is, and we probably already know what a Mars or moon looks like. At least we think we know what it may looks like. And but the thing is, the diffusion model can combine these all concepts and put them together to construct a totally new image, which may be pretty much we can certain that it is a total a novel or new composition. At least it is a new composition. And at the same time, we can verify the how real or how photorealistic or artistic of this image is. So that's the purpose. But because a lot of like astronaut riding a horse image has been generated, you can see tons of them. If you search from Google, you can probably see a lot of these images, or like right here, a lot of images. So right now, this prompt, so the benefit of using this prompt is almost finished or gone. So let's just put it in a historical remark. But it's still fun to actually try this or this prompt. And of course, you can try other things. But this is not the only diffusion model. I mean, Flux is not the only, not even the most modern one. So we can see there's a lot of different, if we just check the zero spaces, but you can see that the Flux is still among one of the most popular one. But there are also like a video generator or like other models, like STXL Flash, or maybe like let me try to find this one is a text to speech model. Okay, this is an instant character. Okay, personalize any character with a scalable diffusion transformer framework. So you can choose customize any photo. So after upload a character image, removing the background would be preferred. Enter the text prompt that describe you hope the character does, and do that. Also, let me um um generate a character. Uh, I'll allow this diffusion model to a realistic, photorealistic. Okay. I'm not entirely convinced this is a good idea. Let me save this image. Okay. And let's go to the other space and okay. So I also need to give a okay, riding a bike in the snow. That sounds okay. So let's generate it. You can see that it is running. It may take like 17 seconds. If it, according to the last time, it runs like 17 seconds. But apparently it has already passed 70 seconds. So let's wait a while. Meanwhile, let's check other popular spaces. The Lumina brush, Flux is still Uno Flux, and frame pack, which is a video generator. Which okay, so you can see that we got this one. We are trying to use this character. Unfortunately, we cannot see the face. Maybe you can run it again. You can try it because um, it it has you can try it for free on Hugging Face. Just search the Hugging Face space for the like instant character flux. If you haven't tried it before. Okay. And another thing is the frame pack, which is a new image, or like a video. I mean, video generator. For this one, you need one. Let me use this again. Okay. I'm using a similar. I'm not sure how long it would take, but let's try it. So it may take a while. So we are not going to wait it. Just firing and maybe we'll check it back a little bit later and to see what happened. But you can see that it does take a while. And in general, the sense is that even if we haven't introduced what the diffusion model is, you may already have an idea that a diffusion model can generate certain things. Sometimes it may take a while, and it can also take things like a text prompt or other material like in this case, the image, or like in the instant character things, you can take a input image as a condition to generate. Okay, the video has been generated. It's faster than expected. So we already generated one small clip of videos. Only take like, I mean, the length of this video is only like 1 second. I believe that we can extend it a little bit. There might be some parameters that we can change to make it longer. Okay, it is still sampling. Currently it seems to only have like okay, 2 seconds of movement. Okay, not too bad. The quality is okay. It's just very short video, but the quality is okay, kind of okay. So anyway, the diffusion model has been one of the tools that has to use to generate multiple different things. So right now, the current trending thing is to generate video. For generating like images is already sort of major things in some sense. So people has a lot of different trick to do that. But in this case, people are currently interested is to generate videos like this one in other different ways. This is quite already this type of quality for short video is quite popular and doable in or by using many different models. Okay, so how does this diffusion model work? How does it work, and why is it so efficient? So that's how the topics we are going to explore today, and in the following weeks. But in this week, we are more focusing on the theoretical part. So it will be a little bit sort of boring or like a little bit tedious if you are not familiar with receiving or learning things by mathematics. But because it is a large part of it is rooted from like physics, mathematics, or like statistic or probability, like differential equation things. So if you just overlook that part, it will be you're missing a lot of different part. You will not fully understand what the diffusion, the context of diffusion model it is, and why, what is happening to the later improvements to it. So it is a part that cannot be bypass or overlook。好，所以我们今天首先会先介绍比较偏向理论和那个所谓的比较理论的部分了啊，比较理论的部分啊，理论呢，但如果你不太喜欢那些数学，或者是说其实也多半大家也不是不喜欢啦，但单纯的就是看不懂嘛啊，单纯的就是看不懂他在讲什么，也谈不上喜欢不喜欢，就是不懂而已。那不过这个没办法的事情，是因为 diffusion model 它有一大部分就是物理数学啊这一部分，因为它的名词就是扩散，那扩散就是物理的那个扩散的那个一个 process 有过来的，所以你没有办法跳过它。然后而且你不晓得它原来脉络的话，后面它的那些改进啊，那些就对来说就没有意义。那你可以把它完全看成就是 auto encoder 啊，你就 denoise auto encoder 只是叠在一起，也可以这样看了。但这样就你可能会少看很多东西。好，所以我们今天主要还是会以比较偏向理论的方式来介绍。那之后的话会就因为它发展到一定的东西，它其实后来跟它原来脉络也会有点脱钩，那到后面就会比较少一点点。但今天的话，就会针对它的理论的脉络和来源来说明。Okay, so let's in today's topic we'll start with the two two fundamental or like a basic approach to the diffusion model. Although there are other modern approaches which is quite different, but the two approaches as one is a denoise probability denoising diffusion process, DDPM, is one of the approach which will start first. And the second one is the score-based model. You can see these two blogs for detail, or you can see this 2022 tutorial, CVPR tutorial. And if you check into the sections, it has a slides and the recorded video, which is quite good. If you check into the different sections, so the first two sections, one is the denoising diffusion probability model, or DDPM approach, and the second part is the score-based generative model. So these are the two approaches that I just mentioned. So these two are the roots or foundations of the diffusion model. But there will be more like more modern and more advanced techniques as well. But today we'll stick with the foundation, with the original one, so that you can have an idea of what it is. So these two blocks are pretty good. The first one is pretty much for the score-based things, and the second one is for a more general approaches combined together. But we are using it to introduce for the first approach, the DDPM approach. Here is a list of important papers for the developing of the DDPM. You can see this paper start from like 2015. Although back then I did not know. I mean, we can check this paper. You can see the result of this paper. This was quite early. So as early as like a game model, like a generative adversarial models, it was beginning like 2014. So it's just 1 year later. But the generated things is not so good comparing to the, if it already achieved a quite good result, then probably we would know it a lot earlier. But the thing that the game gains more popularity back then is it can generate better quality images for a quite long time. You can see that here, the model can only generate simple things like the image images for not in a okay quality. This quality is not so good. It's not too surprising or just so qualities. You may also say that it generates like things like these guys or like more color image like this one. So the generative quality is not amazing, just okay, and definitely not comparable to what the games can do. So it is like 2015 and to the 2019, but it already lay out most of the foundation of the things. But in 2019, 2020, it developed really quick, and early adopters or researchers may have already noticed about it. So that is probably the time I start to notice it. And so several different methods has been developed by these papers. But this paper actually has already catch people's eyes. And I think when this paper has been published, most people has already noticed that, okay, it is already done. Before that, the primary method for generate image is GAN. People use a lot of different GAN. There's like thousands of papers about the GAN. this paper, after this paper, maybe some researchers has already feel it in like previous papers, but in this paper, it has very good evidence showing that the diffusion model has taken over the place. Although the general public has not yet seen it, but if you are doing research and following up the current trend or development of these technologies, this is already since has already done. If you see this paper, you know that okay, the fight is over. The diffusion model actually win. 好，所以其实到这篇大家就已经知道 diffusion model 赢了啊，差不多了。虽然真正在就是迟早的事情，so sooner or later diffusion model is going to win. But the true or like the chat GPT moment of the diffusion model is more like the stable diffusion, which we probably will cover later in today's lecture after we discuss the foundation of these models. But in this paper, you can see that the quality is comparable or surpass the other method like big GAN or like style GAN or other models. It already generates comparable, since just a little bit, but comparable result. But you can see that it already surpassed the GAN models. The reason why diffusion model win is mostly because it is more scalable. The GAN is very difficult to train. It is very difficult to train the GAN. Even if you have a lot of data, a lot of machines, it is very difficult to tweak the hyperparameter to make the GAN training stable. However, diffusion model is much simpler, or at least more stable. So if you have a lot of GPU machine, a lot of data, you can almost certain that you will achieve better quality, no matter what your model is. I mean, better model, better model architecture will make inference faster, make the training faster. That's for sure. But even though if you still using the same model as others, you only provide a better data set, a larger and better data set, a lot of GPU time, you can still get a better model. So the scalability is one of the key reasons that the DDPM, the diffusion model take over, but the GAN left. The GAN can, theoretically, GAN can still utilize a large data set, large GPU might work. It might just work. It's just difficult to train, so nobody have actually can achieve the qualities of what the diffusion model can do today by using GAN. Big GAN is one of the attempt to try to adopt the GAN to a large data set. So by the name Big GAN, you can see that it is big. But still, Big GAN, when you try to actually train a Big GAN, it is very tricky to make it actually work. In fact, in the Big GAN paper, it also do some kind of early stuff because the quality is going to be going downward or degenerate if you train too much. So it is a really big, bad sign that it is not that scalable. So anyway, if you want to remember one key point that why diffusion model beats GAN eventually, as you see nowadays, it is diffusion model is more scalable, and we are in an age that we can have a crazy amount of GPU machine and data. So that's why diffusion model take over. Okay, so we have two different approach. One is the DDPM approach, and the other is the score-based model and the score matching approach. I put a summary on this lecture note, but I'm going to follow in the blog post that I list above so that you can have a more detailed view. But before that, you may see this graph a lot, this illustration a lot, and this is probably one of the things that you will see in the media or popular science way of introducing what the diffusion model is. We'll begin with this very rough and like a more simple model of what the diffusion model is. More intuitive, kind of more intuitive. A more intuitive illustration of what the diffusion model is. So the basic idea is that we have an image and we progressive. We have two processes. One is the adding noise process, and the other process is by denoising the process. Okay. What we are saying, we are not lying or we are actually telling everything we are saying here is truth. It's just we left some details so that there are not the detail is not enough to actually help you to re-implement, and it miss out some crucial part or the interesting part, but it still give you a rough idea of what the denoise model is, and kind of give you some intuitions, especially if you have some mathematical training or background. You probably can come up with similar idea or tools to actually have your own version of the diffusion model sense. 好，所以我这边先讲一个比较概观的，就是你可能在比较像科普介绍啊，或者是说新闻里头，也许有看到类似比较简单介绍 diffusion model 在讲的样子。好，那这边是比较概观，它没有错，但是它去掉了一些有趣的细节啊，不过它可以给你一个比较大的一个 overview， 说 diffusion model 到底长什么样子。So begin with an image. Basically, begin with an image. The forward process is to introduce a noise into this image. To introduce the noise into this image. So we progressively add some images. Noises to these images to a point that it becomes total noise, like a white noise. Okay, what does it mean by white noise? This is a terminology. I'm just not trying to be cute to say something, but white noise is in fact a terminology. White noise, you can see in like Wikipedia. So what is white noise? The white noise is in fact just independent, a bunch of independent normal noise, normal distribution. So in our case, each pixel is identical independent random noise. And each random noise has a distribution that is normal Gaussian or normal distribution. So this is called the white noise. The reason it's called the white noise is because when you look at the spectrum, I probably you will see that in the spectrum, because it is so random. So the this is waveform, but if you look at the spectrum, okay, you will see that it is very like a bend or like a angle, because it is just so like a uniform. It's very uniform. So it is uniform in each of the frequency. So that's why it is called the white, because it is uniform in each of the frequency. 好，所以它最主要是你可以看到这边有个 flat spectrum，它之所以被称为是 white noise，是因为它的 spectrum 是平的，所以看起来因为白就像白色的光是所有颜色的混合嘛，所以每个都一样。好 ，so there are also some other color noise like the pink noise, or like I don't know, but the most popular noise is called white noise. Not every noise is white noise, but if you are totally like a bunch of Gaussian noise, put them independent together, then it is called the white noise. So that is exactly what the target is. So we have predefined a step length like the capital T, maybe like 1,000. At the beginning, it's more like 1,000 things. Of course, in the end, it is more like a 4-step or 10-step. Even for like videos, probably you will use like 15 or 20 step only, not 1,000 step. But I mean, when we consider about theory at the beginning, this T is, you can imagine this T is like 1,000. It's like 1,000, maybe even more, but typically 1,000 is a good number. So start from x0, x0, and you progressively add noise and get x 1,000. So that's the forward process. The interesting part is by using mathematics or like some certain like we develop for physics or other like diffusion things. There are tools that you can use to actually reverse this process. There are some tools that you can use to reverse this process. So these models we are training on these things. This process we can train a neural network model to mimic or to learn the reverse process. So the reverse process is the denoise process. So each step of the denoise process, we get an xt, and we are trying to find out the distribution of the conditional distribution. You can see that the conditional distribution from xt to xt minus 1. We can get this one. So this actually depends on the data. Because the whole process, we know if we already got one image, we know how to add noise. But the thing is, at the beginning, the sampling of x0 is sampled from a distribution that is supposed to be kind of difficult to actually modeling. So that's why we need a neural network model. So that is something we don't know. But each step we are kind of familiar of what it is. So by combining, which we'll talk about it, some mathematic tools we and some learning method, training method for training neural network, we can reverse the process. So each process turns out each process is kind of like a denoise autoencoder. Okay, so if you want to get a very rough story, that's the story. So let me use the Chinese to rephrase it again. 好，所以基本上来说 ，diffusion model 你要从很概观的角度来说，它还蛮简单的，就是像我们刚才的，加上一些杂讯，然后每一小步就加一点点杂讯，加一点点杂讯，加一点点杂讯，然后这大概1000步嘛。然后呢，我们要把它倒回去。那倒回去为什么可能的呢？因为理论上来说，假如我们知道所有事情，因为我们知道它的几率分布嘛，那你就可以，你有工具可以倒推回来，因为它的几率是存在的，那其实是你可以算得出来的。其实真正的麻烦是，我们不知道原来的 distribution， 就这个图片 x0 是怎么弄出来。一旦你 x0 知道，你加杂讯进去之后，这些事情我们都知道，每一步都知道怎么做。啊，那倒退的话，其实就会跟两个东西有关，一个就是你原本的 x0 怎么抽的，哦，因为这个条件几率嘛，就有点像是贝氏的定理那些东西的，你必须要知道它原来是怎么来的，哦，就原来它的可能性大概是什么样子，然后所以这是一开始 x0 是怎么来的，然后呢，你再依照，因为我这个程序本身是已知的，我们只有这个东西是未知的，所以假设你这个原来的 distribution 你都完全能够掌握好了，你是一个比如说很简单的一个 distribution， 那其实是算得出来的，但是问题就是这个 distribution 是不容易算出来的，啊，可是没有关系，我们还是一样，假设他知道的情况之下，我们来算，我们是可以推得出来，但是因为我们不知道嘛，所以我们把剩下的东西就用机器学习的方式，就是去训练神经网络模型，把我们不知道的东西，反正就丢给那个训练的机制，让它去训练，啊，所以最后配上数学配上模型训练，是可以让整个那个程序基本上让它可以反过来，达到一个 denoise 的效果。Okay, so once we get the denoise process for each step, then how do we actually use it to generate things? The key point is x1000, x1000 is entirely random. So we don't have to get the original image to actually following the forward process to actually get this random noise image. We start from a true randomly initial images, and we just simply run the denoise process. We'll see that when we get a prompt, then we can use this prompt to guide the diffusion denoising process. But currently, although in the practice we almost always use the text prompt. Currently, you can first consider the unconditional case. We'll talk about the conditional, how to do the conditional later. But currently, we are not focusing on the conditional part. You can think this denoising process is unconditional, which means we try to generate an image, just a random image. We want anything, any images that looks kind of realistic, genial, realistic is fine. We are doing an unconditional image generation. But anyway, because we have the denoising process, we got a solution. I mean, the noise image. Although in the original diffusion process, this noise image is generated by adding noise to some real image. But the good thing is we don't even need to care about it. We simply generate something totally random. And we're following the denoising process. If the mathematics or everything is reliable, we are likely to get an image. Although we do not have any control of what the content is, but eventually, after this process, the noise process, we are getting a faded looking image generated at the end of the denoising step. 好，所以基本上就是它有趣的地方，就是因为 XT 原则上跟真正的随机的图片没有区分，所以我们真正在生图片的时候，我们根本就不用管 forward process，我们直接拿一张全随机的图片，然后就看看它会发生什么事情。那最后证明，其实它其实是会成功的，因为那个几率，照它的道理来说，它本来就会跑回跟原本 X0一样的 distribution， 它不会跟一模一样的图片，但是它会跑到一样的 distribution。所以用这种方式就可以生出图片出来。Okay, but there remains a lot of details. Also, after you get this explanation, if you feel this explanation is satisfying, I mean, when you see the this guy, I mean the image we generated or the things we generate, you probably will feel like a little bit like curious or like wondering what is going to happen because you don't know what's happening. You want to know how it works. So you need something to actually answer or to fulfill your curious. So I believe that this like very intuitive, very rough explanation can solve some of them. 所以当你看到那些，当你学东西的时候，比如说这个 diffusion model， 看到生图片，你会觉得它很神奇，你会想知道它是什么原理。所以刚才的那个解释可能可以回答你最原始的、最基本的、最大的一些矛盾和就是你的好奇心或不解的地方。So it may answer certain the certain big part of your curiosities, but the thing is, it is not going to be enough because based on this understanding, there are still a lot of details or mysteries remains. For example, what is exactly the process of adding the noise? What is the detail of the process of denoising? And something is more fundamental is why, I mean, it looks kind of reasonable, but why does it actually what is a key point? What is a crucial point to make sure that we know that it is going to work? So there are a lot of detail. So that's why we are going to talk about more about the mathematical details about it. So let's first check the first approach here from this blog post right here. Okay, so this one is pretty good blog post, and it is keeping update for many new, more advanced techniques and the things. At the first, it has a pretty good graph to showing compare the diffusion model with other generative models. So, for example, we have already seen the variational autoencoder. So it has an encoder to encode an image. Let's first focus on generating image. Although the principle apply to other materials like video or even text. Okay, so for a variational autoencoder, it first has an encoder and generate a latent, and this latent pass through a decoder, and we contrast this image x prime. So the goal is to make x and x prime to be the same. That's the key idea. For flow-based models, it's pretty much the similar. We use x to use a flow model when X image pass from model to another domain, and then this domain we have an inverse to get back to this image. The difference is that in the autoencoder, it all usually has a bottleneck, so that the encoder, the dimension of the latent space, usually much less than the original space. So this is autoencoder. But in a flow model, the dimension of this X and the latent are usually the same. That's why here this is a rectangle, not like here. This is more wide, it's narrow. They have the same length. So what's the difference? Why do we need a bottleneck but in VAE but not here? The thing is that the flow model does not train. We don't need to train a decoder and encoder pair. We train only the flow, and the inverse come up automatically. The reason is that by design, this flow model is reversible. This flow model is reversible. So there are more restriction. Usually there are more restriction on the design of the architecture of what the flow model is. So the restriction is not on the bottleneck, but on the architecture itself. And the similar thing is the latent Z is usually assumed to be something we already know, like Gaussian distribution. Okay, in here, the default diffusion model. Okay, but anyway, the encoder, decoder are both need to be trained. And for a flow model, only the flow need to be trained, and the inverse comes automatically. In the diffusion model, there's a forward pass for adding noise, and the backward part, the reverse part for removing for denoise. The forward pass is not going to need to any train because we already predefine it. We are only need to actually train the reverse part or the denoising part. The denoising part need to be trained. The reason that denoising part need to be trained is that we don't know the original distribution. So although we fully understand what the forward pass is, unlike the flow model, the inverse part does not come automatically because it is more like a more probabilistic things. It depends on the original distribution. So we need to do the training. The similar thing is that eventually we want this latent to be none. Like the VAE, like the flow based things like here, all these things is going to be the latent need to be none. It's nonsense. Okay. But different and also a similar thing is the dimension. You can see that dimension, like the flow model, they keep the same from the beginning to the end. The dimension is keeping the same, unlike the VAE model things. Okay, so for again, it kind of like the VAE. It is a wide, narrow sense, but it serves differently. It mostly focusing on the generative things. So the latent is usually none. Forced to be none because it more focusing on the forward pass. In the VA case, like we see before, the reason that we know that the Z is going to be like normal distribution is we have a loss on it, so we can, after the training, we kind of forcing the latent to restrict it on to align with the desired distribution. But in here, again, we begin with generate things with a given latent distribution, like a normal distribution, or if you want to use uniform, it's also fine. So we start with it and generate something and try to make change the model to make this generation to more align with the target distribution. The discriminator is used to as a metric to measure difference between this x prime and the x. So you can see that we have x prime and x, and fit them into a discriminator. So that's the differences between them. But typically, the latent has a lower dimension than the output x. Also, you can see a quick glance of these 4 different popular methods for generate image. Okay, so what is diffusion model? So let's first look more details into the forward diffusion process. Okay, so here I'm going to show you the mathematical formula. 好，所以我们这边的重点是我们要看这个数学式子，然后跟刚才的那个观念把它连在一起。So we'll connect to what we talk about adding noise things, and how do we actually do this in a practical way, or what we actually do since in the code or in the computer and related with this formula. So let's begin with this formula. You can see that here. But before that, let's move a little bit downward here. So this is the graph we have already seen here. Start from x0 to xt. So each xt is a progressive noised image from the original one. Okay, we are only focusing on the forward process. So using this q to represent the probability. Q xt minus 1 xt. So this guy represents that, okay, we are considering a process that has some randomness, and we begin our input is xt minus 1, and our output will be xt. 好，所以这边的 q xt xt minus 1看起来很复杂，因为有一个 condition 那个符号嘛，一条线那边大家可能有一些阴影或什么的，然后就会觉得有点害怕或者不熟悉啊，然后也不晓得它干什么，又有一个新的字母出来，每次碰到一个新的字母，可能大家都很紧张。但是这个的意思，其实这边的资讯没有很多，这边的资讯只有告诉你，我现在要做的事情就是这个东西是一个 process， 一个步骤，这个步骤它的输入是 xt 减1，输出是 xt， 然后它有一些几率性质在里头，它是有一些随机性质在里头的。So what this process is, basically, I'll show you a detail a little bit later, but basically, it is something looks like this one. So for x pixel, this is an image. Say this is xt minus 1. And after this process, we are getting another image which is called xt. Xt and xt minus 1 is pretty much the same. But for each pixel, we are doing something. For each pixel, we are doing something independently. So when we do something on this pixel, it is totally independent to what we are going to do it on the neighbor pixels. 好，所以这边有一个重点是我们每一个 pixel 都独立去做一个 random 的事情。好，本质上来说 ，so basically there's one thing. What we are going to do is a little bit more complicated than what I'm going to say, but you can imagine the easiest or more simplest things we can add noise is to actually add some noise. Let's just say it is a normal distribution, like 0, 1。好，你可以加的最简单的事情就是在这个 pixel 上面加一个简单的，比如说是 random normal 那个高圈 distribution 嘛，一个常态分布。那可能不要这么多嘛，因为有点大，可能某一个那个什么一个尺度啊，加一个贝塔倍上去，就这样子而已。对，原则上来说，我们其实就是我们想做的事情呢、基本上就是把这个 pixel 加上一个小小的 noise。So basically, the simplest thing we can do is to add some normal distribution, some Gaussian distribution independently on each pixel, and to make things even simpler, each distribution is identical. So that's why we call it IID. That is identical independent distribution. When we write IID, it doesn't mean that we are creating a terminology to actually to make things more complicated. Quite on the opposite. When we write IID, which means okay, you don't need to worry about too much about it. We are considering the easiest setting. 好，你会常常看到 IID 这个词。当你看 IID 的时候，如果你不熟或者一直对它有点排斥，你觉得哇，这个又是一堆抽象什么的术语，但不是 IID 其实意思就是说，好了，我们现在因为很多可能性嘛，但是我现在告诉你的就是，我们现在不要考虑太复杂的可能性，我们考虑的就是最简单的，反正你每个点就个别去做它的事情，我们中间也没有什么关系，然后也不用考虑说会不会这个点用这个杂讯，另外一个点又不一样的杂讯，不会，全部都是用一样的。所以 IID 的两个 I， 第一就是 distribution 而已啦。那 II 呢，就是 ID 就只是分布嘛。那 II 呢 ，II 指的一个是 identical， 每一个点都一模一样。那 independent 就各自点不独，就是各自是独立的，我不会影响你，你也不会影响我。所以事情是简单的。所以如果你要加杂讯，最简单的就是你可能就是加上了一个随机的杂讯，直接加上去。So this ID is a most easy way to add. I mean, if you just add the noise, it is kind of like this one. However, I mean, if you want to write things like in NumPy, it is probably like xt minus 1 plus, okay, like np dot random probably like randn. This n means like normal distribution. Randn means like just normal distribution, like 0, 1 or 0 something, little beta. And that's it. You probably will have the same shape as xt minus 1 if it is an image. And you just add every random noise on it. Then that's it. So if you're using NumPy, it is that simple. However, the actual formula is a little bit more complicated than this one. Just a little bit. So the actual formula is this one. Okay. So this one is the actual formula. This is a normal distribution. So not only we are adding some noise to it. You can see that this is still a normal distribution. And there's I here. This I means the identity metric, which means we have 1 on a diagonal and 0 otherwise. This indicates this is independent. This is independent. And because beta t is like a beta we use here, but it depends on the step. So each step we consider it separately. But by given t, if you already have a t, this is just a scalar. It is not a vector. which means this scalar works on every pixel. So when you read on at here, you know this is IID because beta t and I. Beta t means it is identical because it is just one number. If you have to do it differently on each pixel, you probably will have a lot of different parameters for each pixel. But okay, nobody would do that. And we actually have just one number. So this is why this is identical. And because this is a big capital I here, we know this is a identity matrix. So we know it is independent. Okay. Let me get the. Do I have a eraser, or maybe I can just. Okay. Let me just get a eraser. Okay. I want to just want to remove everything. Okay. So here. Okay, let's do it again. So we know that this one is just it is ID。所以我们读到这边，你看到这个贝塔 t 跟 i， 其实它是简单的原因是因为 i 是那个对角，就是 identity 的单位矩阵嘛，所以它是简单的。然后贝塔又是一个数字而已，所以这边是简单的。它只要它没有要做很复杂的事情，它只是要做一个加上杂讯的事情。So the only difference is that okay, the only difference is here. Instead of like if we are writing things like n x t minus 1 beta t I, then this is exactly what we described before. We are adding some noise to it because this one is just like xt minus 1 plus n 0 beta ti. You can see that the xt minus 1 plus some noise. This is what we described before. But the things, it is different. This one xt is not important. This only indicated that we are describing the distribution of xt. Because here we have a xt right here. So xt does not matter. The only thing matter is here. We have this guy. We have a scalar on the xt minus 1. So not only we are adding some noise, we are actually sort of scale down the original image a little bit, or scale down it a little bit, and add noise. 好，所以这边的差别就是这边多了一个这个东西。那这个意思就是，你可以把它看成是我们把这个图片稍微乘上一个小一点，乘上一个0.9啊、0.95啊这个数字，拿出来变小一点点，再加上 noise。So like I said, it is just a little bit more complicated. We kind of scale down the image a little bit. I mean, this scale down is also pixel-wise. We scale down the intensity of each pixel a little bit. How much? Just this much. Like beta is, I can consider beta is a small number. So the square root of 1 minus beta t is like a 0.95, 0.99, something like that. So we scale down this xt minus 1 a little bit and add some noise right here. Okay, so it turns out this thing is actually just equal to things like xt minus 1 times a scalar, which is 1 minus beta t. Okay, and you plus some normal distribution, 0 beta t I. So that's it. So why do we even bother to actually scale down the intensity of each pixel a little bit? The reason is that if we scale down it, we want to scale down it to a point so that the effect of the original image does not appear at the end. So if we simply just add some noise to it without the scaling, then it probably will kind of like a random word and still keep certain track of the original image. But since our purpose is to finally get a totally random things at the end, so by doing this scale down, we will increase the speed of kind of removing information or making the xt to be totally random。所以这边的其中一个作用就是要让它快速的消失掉它的这个所有跟原图有关的资讯，所以让这边变得完全的随机。这是我们的希望得到的重点。所以他会做这个东西的原因在这边。所以你在那个程式码的其实你会看到。好 ，OK， but even if we want to do so, why do we actually need something like a square root of 1 minus beta t？ 好，就算我们要做好吧，你说就算我们要做把它变小，那为什么不用另外一个变数就好了？就或者是一个常数嘛，干嘛用个贝塔 t？ 那这样感觉很不舒服啊？为什么？因为莫名其妙跑出来一个根号1减贝塔 t， 然后贝塔 t， 这正常啊，就是你会觉得说这个东西莫名其妙跑出来，但是不用紧张。其实不用紧张的原因是因为它这个不是拿来考你的。大家可能会紧张的原因就是，如果你看到课本上，以前看到课本上有这种东西，你就觉得说，哦，不知道它怎么来的，到时候考出来，我怎么知道写这个东西？这是不是要背啊？但是这个东西其实都是一个选择。So you can feel this as a choice of the author. It's just as an observation. This is an interesting choice. So the reason that it right in this way is because the computation. You will see the following computation. It will make the computation easier. So mostly because it will make a computation easier. Sometimes, if you don't know how or why this is happen, sometimes it has a historical reason. Especially in this case, because you can see that we have a name called diffusion, and because it is called diffusion, and diffusion comes from physics. You can imagine there are already certain theories and studies, a lot of different things are already done on these topics. So there are quite a history or development or tools as already existed. So there's definitely something that you probably doesn't know already. So this, you can just feel this as a interesting choice. 所以你就把它看成是一个有趣的选择。那也许它有一些其他原因啊，或什么之后再把它补上去，其实注意就行了。但首先第一个 ，so your focus is first understand what it means and why it is necessary. Then that will help you to understand what it happens. Okay, so the reason, a lot of reason is because of computation tricks or things. Okay, another thing is, okay, what if we don't even use this beta? I mean, this scale. We use this beta t like a constant, and we don't use this one. There are certain other approaches. I mean, if you random work a lot of time, like 10,000 step, 1,000 step is already quite long. But eventually, if you go long enough, the original information is going to be lost in certain way. So that might be another choice. So there are not just one good choice. A modern approach has a different choices. There are not just one choices. You just need to observe and notice that this is the choice of this diffusion model. 所以其实当你觉得怀疑说哦，为什么不能用什么其他的方法，或者是说这两边为什么要一样或者不一样，也许它都可以。但是现在这边的话，你首先要读到的就是它这边使用到的是这种选法。如果你认为它是不一定要这样选，不一定要这样选，或者是说你觉得这样选太无聊，我甚至怎么样做都可以，说不定就可以，那你就可以试试看，这可能就是你另外一种方法。假如你的理论过得去或什么的，但这边你要做到的事情就是你注意到这是他的选择，有原因，你知道他原因到某个程度都很好，完全不知道也不用太担心哦，因为这不是拿来考你的，这不是拿来考你的哦，所以不要再就是大家很多时候会害怕这种数学，就是会觉得说，哦，这个为什么会这样子？这要考我太不公平了吧？现在已经没有考试了，这不是要考你的，哦，所以不要害怕，就是读它就好了。你只是读到说，哦，他是做了这个选择，他的比如说你看到一个人的姓名长得像是这样子，他取了一个名字叫王小明好了，或叫什么，这是他的选择，有原因没有原因，他可能有他之所以叫小明，也许有他的一个历史因素或什么，有或没有都不重要，他不是拿来考你的。哦，所以不用为了这个东西去纠结它，哦，为什么一定要这样子？哦，这样考我公平吗？或什么的？它目的不是要来考你，你只要注意到说，哦，他的名字是叫这样子，他的做了这个选择，那中间你知道越多越好，啊，不知道也没有关系，因为这是别人的选择嘛。Also, just notice that this is the choice of kind of like the original diffusion model. It's original DDPM. This is the choice of the noise scheme. Kind of like why do we even use the like Gaussian distribution? Can we use other diffusion? Yes, you can. But this is easier to compute, and a lot of existing tools are using Gaussian distribution a lot. So that's why it is. You can imagine. I think it is a very reasonable choice to use Gaussian because it has encountered it a lot. So it's kind of like a de facto choice of the distribution. So public doesn't complain too much about the choice of the Gaussian distribution. But still, Gaussian distribution is a choice. And you can probably already imagine that the reason why they chose Gaussian distribution. Uh, Other choices are pretty much similar. They are choices. That's for sure. They are choices. And this here is their choice to the like the noise schema. 这是他们选择增加那个 noise 的一个 schema 没有一个单一的完整的一定对的一个选择，因为后面还有一些其他的模型嘛，他们会选择不太一样的东西。Okay, so let's see how it works and see the common terminologies. So first of all, people use alpha T also. So you can see it in the diffuser. Okay, by the way, the code that people use is diffuser. It is one Hugging Face diffuser. It's one of popular framework library that you can use to do the diffusion. We'll probably will use it in the next homework. So if you look into the code in here or in the original stable diffusion code, you will see these alpha beta things there. Okay, so let's see here. The alpha t is equal to 1 minus beta t. So again, this one is to make things easier to do the computation. So instead of calling it 1 minus beta t, we call it alpha t. And we also have another terminology called the notation. Alpha t bar here is the product of all these alpha t, alpha I up to t. So this is called the alpha t bar. So the reason that we use this notion is this notion gives a shorter and more succinct expression of the things that we are going to use. So for each xt, we can easily write the things as this one. The optional t minus 1 is a noise. Sorry. Like what we write before. So you can see that we scale a little bit about xt minus 1. And we also scale the standard normal distribution a bit. So xt can write in this formula as this formula. The reason we need this alpha t bar is because we want to composite several steps together. So that we can instead of running it like a loop of t steps, because the property of a normal distribution, we know that when we add two normal distribution together, we get a new normal distribution. It is still a normal distribution with different mean or different like standard deviation. So it turns out that xt can be simply write in this form, like x0 times a scale and this guy. It is still kind of like the first one, just with different scale factor and noise factor. So we can write in a more formal way, like more like the original one. We can write qxt x0 is equal to this guy. 好，所以我们就把它写成这样子。So these two are basically the same. Basically the same. Because people are familiar with normal distribution, probably it's just one or two steps, and you can actually derive these formulas by yourself. So this routine is quite standard. But the key point is that we can do the multiple step of the forward process in just one step without any issue. 好，所以这边的重点是，我们总共比如说有1000步好了，可是如果我们想要直接跳到第562步，也是可以的。我们不用真的去从 x0 得到 x1 得到 x2，一直做下去，然后得到562。这边我们可以一步就做到。So we can, if we want to get like x532, we don't need to get the x1 first, then get x2, get x3, get x4. We can actually do it in just one go, like this one. This is exactly what happens when we do the training. It's not difficult, but well, it's still something you need to know. And I can imagine some students may be confused of why when we do the training, we don't need to actually loop through like this one. From x0 to x1 to x2 to x3 to x4. We just do kind of similarly simple thing. The reason is that this formula, we can do this thing. So that's why we need a square root egg. You can probably, in the diffuser's code, you can probably see the table of the alpha t, or like, alpha t bar. You got the table of alpha t bar. So that's all you need. The table of alpha t bar is all you need to actually do the forward process to get any xt, to generate any xt dynamically. Okay. Okay. So there's also a thing called the stochastic gradient Lagrangian dynamics. It's kind of like a gradient descent method, or like a gradient descent method. This method is serve as a theoretical foundation of the sampling method. when we do the diffusion model, like a stable diffusion, flux, or things, there's a sampling process. So how do we actually do the sampling? The sampling, the theoretical foundation of the sampling. This is one of them. Is called the stochastic gradient leveling dynamics. It is using to sampling the distribution by given only the gradient. Also, the key is that it's a sampling process, but you don't need to know the full distribution. You only need to know this guy. If you don't know this guy, then you can do the sampling by using a method quite similar to the gradient descent. You can see that kind of like this one. So this is how it does the sampling. But it is gradient descent with some randomness. So it is not going to converge into just one point. So if you are using a gradient descent, it will converge to the local minima sense. This is not what we wish to achieve. We wish it to converge to a distribution. That is, even if it has it is not the most possible choice of the outcome. It still got its fair chance, its fair share of a probability when we do the sampling. So we need to add some randomness. Otherwise, it will stuck to a local minima. So that's why it will introduce some randomness right here. So it is kind of like a gradient descent, but you can see that here looks like a gradient descent. It is a gradient descent with some randomness to it. So the goal is different. It will achieve to converge to the distribution itself, not just to a local minimum. 好，所以这个东西其实是在那个 sampling 会用到，这边特别提了一下。也就是它其实类似那个 gradient descent 的一个stochastic gradient descent，但是它多了一个随机的东西在里头。因为如果你用 gradient descent 的话，它最后就会跑到 local minimum 嘛。但是它这边加了一个随机的，它不会稳定的停在一个点，它会有一个像是几率分布的样子。那这是我们想要的，因为我们想要抽样，然后得到它几率分布的样子。而且我们不需要全部的资讯，我们只需要它的微分资讯。光有微分资讯，我们就可以做抽样。所以这是这个演算法的好处。这个会用在类似就是在做 sampling 的时候，在做 diffusion model sampling 的时候。Okay, so once we already know the forward process, and we sort of knowing that we can, suppose we already have everything, we can do the sampling. So let's focus on the difficult part. That is the how to do the reverse diffusion process. So theoretically, because if you from a gut feel, you can see everything. Because everything has already designed, every distribution has already designed from a distribution view. Of course, the reverse process is already determined by the forward process. 好，所以其实因为假设说你已经知道所有东西都已经被决定了，它 reverse process 当然已经被决定了。But the only thing is it is difficult, or maybe infeasible to actually compute the reverse process. Especially, our issue is that we do not fully handle or have a fully control or handle or understanding to the original the distribution of x0. So that is probably one of the issue right here. But theoretically, here is some demonstration. Suppose this is the x0 distribution. This is the targeting or the distribution that we are interested in. So by using a diffusion process, it will, at the end, will similar to a normal distribution. So if we do the reverse process, we can start from this normal distribution and get back to the original distribution. That is already existed. We just reverse the timeline. And this one can be achieved, kind of achieved if you have enough information. You can achieve by the using the sampling method like the Venn dynamics to do that. Okay, but the thing is, it is difficult to actually formula the reverse process. So let's see what we can do and to isolate the difficulty of the things. To spoil the difficult things is the distribution of the x0. So we'll see that suppose we know the x0, everything should be easier. So that's one of the key points to solve the mystery. So we already know what we fully understand what the q xt minus 1. We fully understand what it is. This is something we already know 100%. Because we already know the formula here. Like we know this one, and we know this one. What we don't know is the other way around, like from xt to xt minus 1. This is the goal, and we need a model to kind of approximate it. So this is our goal, but this is difficult. So instead of doing that, let's do something easier at the beginning. So first we do this guy. xt, x0, and xt minus 1. It is close enough to like xt to xt minus 1, but it is much easier because we got the x0. So the reason is that we already say that the difficulty is that we don't know what x0, the distribution of x0. But when we fix just one x0, like in this case, we start with a specific image. Everything we know already. The process or even the backward process, we know everything all the way. Because we already know, we are already given a specific x0. Suppose we already have everything is going to be zero, easy, because this is independent to the distribution of the whole x0 things. We got a arbitrary or like a given specific x0. Things is going to be easy. So this formula reflect this fact. 好，所以就像前面说，我们如果已经给定 x0 的时候，主要困难点在于 x0 整体的 distribution 我们不知道。但是像刚才前面那个 process， 我们在做的事情都是已经给定一张 x0， 剩下的事情就轻而易举了。所以这边就说好，那我们先试试看嘛。我们先假设我们给定 x0 了。So suppose we already got x0. Everything should be none. Should be none. So it turns out it is the case. It will be this is our goal or our final result. 好，所以这是我们最后的结果。哦，这个读起来可能你如果直接看没有注意看它英文的话，你会觉得有点不晓得它讲什么。哦，但这边其实很单纯，就是我们最后的结果，它的概念很简单啊，就是刚才讲的，你的 x0 如果给定了，事情就不管讲一定算得出来，可能有点难算了，但是一定算得出来。你不给 x0，不可能算得出来，因为条件不够嘛，因为跟资料集有关了。你给不同的资料集，算出来的东西不一样，所以你不给，但是资料集又没办法好好表示，那不可能算出来了。我们先给 x0，它一定可以算得出来。好，那它算出来最后会是一个 normal distribution， 就是你给 xt x0 的。So the result will be a normal distribution. It just say that it will be a normal distribution. And for this normal distribution, the it will be this is going to be the mean, and this is going to be the standard deviation. And the mean is only depends on xt and x0 for sure, because this is something we were given. If it is going to depend on xt minus 1, then it doesn't make any sense. Our goal is to only depend on the condition. Okay, but this says very little things about the probability. It's just very generic things. And this one only says that okay, this is something we can compute, and the standard deviation only depends on the step. Okay, so the following is some computation. I'm not going to follow the computation, but the key point is that it is computable. It is doable just by following this computation. You will see that, okay, no matter what it is, eventually we have a formula that can compute this guy and this guy. Okay, so the thing is, by given condition xt and x0, we fully understand what the distribution of xt minus 1 would be by given x0. The only difference is that we probably have to run over all the x0. But this one is tools that we can do it purely analytically. 好，所以这边的话，基本上就是我们如果好，我们先不要去管训练啊，或者比较复杂的东西，就从前面的 idea， 反正就是给定那个第一张 x0之后，事情就变简单了。我们先把我们能算的算出来。好，它的公式也许很复杂，但是总之它是有公式的。也就是说，我们给定 xt 和 x0的时候，我们可以算出 xt 减1。所以这其实是你在算数学的时候，我们其实没有办法记得这么细啊，没有人可以记得这么细。就它这个到底是什么？我们记得的东西都只有输入什么，输出什么。有的时候你还是要去查一下。当然，你一直在算这个时候，你久了之后你会熟悉。可是通常没有人会记那么多。我们只有掌握到说，什么东西跟什么东西是有关的。我从什么跟什么，我可以有办法得到它什么东西。有一些东西没办法，因为有一些东西是没办法得到，或者你还不知道怎么去得到。但这边是。好，我们得到的结果是，你从 x1跟 x0，我可以算出来 x t 减1，这是我可以做到的事情。Okay, so there's also a nice property we already get before, like from x, that is one step from x0 to xt, and vice versa. So we can write x0 to be kind of like this one. So it turns out if we let x0 to be like this guy, and we can put them to be a single form, like mu t is kind of like this formula. So this is the formula that we want. And by using similar method to like the variational encoder, instead of compute the this is the log likelihood is the thing we want to compute, but it is difficult to do so. But we can use some inequality to bound it. So it turns out we can compute this guy instead. 好，所以我们本来想要算这个啦，但是不好算嘛，所以我们就全部合在一起。就是我们知道这是它的上限，所以我们就去算这个东西。So instead of to compute the cross entropy, the thing we call the variation or the lower bound, right here VLB. So this is the target we want to do. So by this thing, you know that this thing is actually quite. Before we actually go into the detail, you can see that this guy is actually okay or good to compute. The Q1T X0 is easy because this is a forward process from X0 to everything. This one is quite easy to compute. We know everything about it. And this guy is a little bit more difficult, but because this one can be write as a product from X0 to X1, X1 to X2, X2 to X4, and this one is log. Log will separate the product into a summation. So this one is also good. Okay, so this one is another derivation of we don't instead of compute the cross entropy, we compute the VLB like this one. Okay, so to actually compute the VLB, you can see that like I said, the denominator can be written down as a product, and the product can be written down as a summation, which is easier and good. And it turns out that we need to compute a bunch of K diversion of the things. Like in the variation autoencoder, we know that the K diversion of the normal distributions, all of these are normal distributions. Like you can see that this is xt, x0, and xt minus 1 is something we know how to formula it. And this is so we should actually compute everything altogether. So this one is the thing that we our model. This is our model. This is our model, and we want this to be either minimize or maximize the things, or minimize the things. Okay, so we can actually compute everything because of what we already know. So we have even simplify the things because we know that this one is a normal distribution. Everything is a normal distribution. We can simplify the K diversion to actually compute the things. So it turns out the formulas become like this one. This is the loss, the final loss function. The epsilon t and the epsilon theta. Epsilon t is the actual noise that we generate when we do the training time, and the epsilon theta is this is the model. You can actually see this one will be easier. This is our model. Our model take one input like xt and the step. 好，所以这是我们的模型。我们模型是要预测它的 noise。那它的输入是什么呢？它的输入是 xt 和它第几步？你要知道它第几步嘛？还有它已经被加上 noise 的图片长什么样子。So we got the noise image and the step, and we want to predict what the noise is. And you can see it turns out it is just a square error, with some weight, some scale, some weight right here, kind of complicate. But this scale and weight is determined on the like alpha t, alpha bar t things. So this is the original loss term to minimize the loss of the diffusion model. The key point is this guy, but it also has other terms as the weight. And this weight depends on different step. This one is just expand of xt into this guy. But in 2000 following up paper, it actually removed the scale part. The reason is that every step is not equal. Some steps are more important than the others. Usually the step is more close to like x0. The smaller step is easier. I mean, is important. you can do pretty. I mean, when you do at least when you do a training, the step are near 1,000 or like 2,000, like 500 is less important than the step that's very close to zero. So they maybe have when we're training, we may want they have different weight, and this differences is kind of independent or to the formula calculation above. We will have to introduce certain weight anyway. So this weight, maybe we can just forget about it of all. We can just ignore it to introduce our own weight. Okay, so anyway, so the simplified loss is become this one is suggested by this paper, and it totally ignores the weighting terms and seems to be training quite well. So there is something that you will see in the code, like in diffuser or in other thing. 好，所以这是你最后会看到的。你会发现 ，OK， 哦 ，so it looks just like a denoise autoencoder, right? We predict the noise. We got a noise image like XT and predict the noise. So it's kind of like a denoise autoencoder. So if you forget all the context, all the derivation, all the things come from, it is just a denoise autoencoder for multiple steps. That's it. But it comes from what we see before. 所以它前面一大堆的那个脉络啊，那些东西就是刚才讲那些东西。那如果你只看程式码的话，你大概就会觉得 OK， 这没什么啊，就是一个 denoise autoencoder，但其实它是从很远的地方来的。好，那原因之所以从前面的话，都是化简而已。So above that is just all simplified from mathematical formula. But from here to here, is because of this paper. So this one is do the training. The training algorithm is quite easy. Despite of all the long theoretical and derivations, the training algorithm is nothing but this one. Okay, so first of all, we take any x0 from dataset. So this one is from the dataset. And we take one of the uniform step from 1 to t. Just pick random step. Choose a random step. And we construct a random noise. Okay, now we add the noise to get xt. So we use this combined formula to construct xt right here. I mean, the guy in this parenthesis. 好，所以括号里头这个东西，这是 xt. And this model, epsilon theta, is used to predict what this epsilon should be. Okay, so we run a gradient descent on this one and until it converges. So this is a training process, pretty easy. And if you really look into the training loop in the diffuser, it is not difficult. It is as easy as this one. Okay, so then how about the sampling? Sampling is following similar things to the like the dynamic things. So for each one, we start from totally random. You can see that little I, it is a totally random thing. There are some details. There are some if you especially if you are using a stable diffusion or latent diffusion, there are some scaling to the latent. But basically, we start from xt, which is a totally random image. And every time we run the sampling step right here, and for 1,000 step, and we get, you can see that this one looks like the denoising process. like a denoising process, and like the Vino process. But if you really want to look at it, it is the denoising process. Okay, so this is one approach. There are a lot of different, technical details to do computation. Another approach is called the score matching approach. That is, you can see the noise condition score network. It is more elegant and a little bit more mathematical oriented because it uses some like stochastic differential equation, but it will also give you a lot of intuition of what it is. 好，所以这边我们再很快速的介绍另外一个 approach。好，这个东西主要是从那个 score matching 的地方来的。好，这边我从我的这边直接讲就好了。You can look at this blocks. It has a very good details about it. But let me do a quick version, quick introduction based on my summaries of the things, so that we can through this one faster. Okay, so first, suppose our density function. So it kind of like what we do with the variation autoencoder. We are not thinking about diffusion. Although it turns out we are going to get the diffusion model quite at the end eventually. But at the beginning, we are not thinking about the diffusion model. We're starting from the likelihood. We start from the likelihood. We're not thinking about diffusion. So first of all, let's think about the density function p theta. We can actually write the p theta as an energy function, like this one. So why do we want to write kind of like this one? The thing is that exponential things like this one is going to guarantee it to be positive. And because the denominator is kind of tricky to deal with, so we're using a normaling. This is called a normalizing constant. This is called a normalization constant. So this one is a very popular formulation of density function. We put the difficult part to the normalizing constant. This is called the energy-based model. 所以这一种的 approach 很常见，就是我们要把我们的 density function 写成像刚右边这种形式。分子的话就是 exponential 的像这种东西，那你的模型就是 f theta。好，那 f theta 你就可以自由。它的好 ，the benefit of this approach is you can have a freedom to have your model. You don't need to worry about it is positive, negative, or anything. Any model should do, because we're using our interpretation of this model is to put it through exponential and divide by a normalizing constant. So this is called the energy-based model. Very popular, very common technique to do that. But the difficult thing is usually we don't know how to. Sometimes it is infeasible to actually to compute this normalizing constant because it is difficult to compute the integration of the exponential of everything. 好，所以它困难点通常是它的分母这个 z 西塔很难弄，但是假设它存在，大概就长这样子了。Okay, so then we can train it by maximizing the local likelihood. This is still something we want to do. And because we are using the log likelihood, by taking a log, the z theta is usually the trick is the typical intractable part is going to be log and to be become a separated term. 所以优点就是一旦你取 log 之后，这分母就跑右边去了，然后就被 log 掉了嘛。所以这很常见，就是我们要用 energy base 的话，常常就因为配上 log likelihood 就会这样做。So this theta is usually intractable, but in this case, we are taking a log. So it is kind of like what we do for the VAE. So like in VAE we approximate the normalizing constant. That's what we do in VAE. Or in this case, we are restrict model architecture to like what we do like a flow model. 好，所以有的时候我们有不同的做法嘛，就是像因为这是前面是比较一般的状况了，那你在 VAE 也是碰到类似啊，然后你用 flow model 其实也都是类似的事情了，只是他们有不同的方法来处理这个问题。那 VAE 的话就是去近似它，然后那个前面讲到 flow model 嘛，它的那个模型结构比较有限制，它的限制是在模型结构上面，所以它的模型结构必须要能够有特别的设计，所以能够控制这件事情。The score function in here we are using score function to bypass the difficulty. Okay, so 它的万恶根源就是它这个 z 西塔很麻烦，那就有不同方法来去弄它。Okay, so 就有点像刚才那个，其实基本上就是刚才说的那个 the Fana 那个 dynamics，我们可以就不要知道 p 本身，我们只要知道 log p。如果我们只用 log p 就可以算出来，就可以做 sample， 那就不需要知道分母了。基本上是这样子了。Okay, so here we are only consider about a score function. The score function is defined as the gradient of log px. Because we are using a gradient and using log px, by using log px, the z theta is going to be another term. And by using a gradient right here, this term finish. Because we are using a gradient on x and z theta does not depend on x. So the score function is defined as the gradient x of log px. The name of the score function is come from statistics. So there are some variation on these definitions, but here we use this as a definition. Thus, we would like to have a score-based model, or let's just call it S theta x, to be defined as this guy. OK， 这只是说这是我们的模型，我们要来，我们有个真实的几率啊，那这只是我们模型，然后这是我们定义，因为有 S theta，所以我们叫 score-based model，然后这个叫 score function 嘛，他们叫 score function。And because S theta x is equal to this guy, so we get rid of the intractable z theta. So that's the plan. That is the plan. So therefore, we can train a score-based model by minimize the Fisher divergence between the model and the data distribution. So the Fisher divergence is one of the measurements between two kind of like Taylor divergence. But Fisher divergence is also quite common to use. So this is a definition of the Fisher divergence. Okay. This is what we want to evaluate. However, it's still difficult to actually know what this guy is. Right? If we know this guy, what this guy is, we don't need approximation. The first reason we want to use approximation is we don't know exact formula of this guy. So how do we actually compute this divergence? The thing is we use some mathematical tricks, which called score matching. 这边其实就是用了一些数学技巧了，就是说你不用真的去算这个东西，就可以算这个东西了。他用so you use some calculus tricks to has a workaround to do that. And finally, we can use the Lavena to do the sampling. But please note, even at this step, we does not see anything about the noise or adding noise or denoise, right? We're just saying the score match. We are actually just to get first, we get rid of z theta by we getting of z theta by using the log and the gradient, right? And we are using the Fisher diversion. Like I make a prediction that we're going to use a mathematical calculus trick to actually to compute. We can actually compute this divergence. But right now we are not using anything similar to a noise or denoise. The calculus trick is called the score matching, which we will see in a very short time. Okay. No, we are not going to do the detail about the trick itself. We'll discuss it a little bit, but this the point right here is why does it related to the noise denoising autoencoder? It is because this the thing dynamics. Because before that we are only focusing on the score function. The score function is all good, except it is not the distribution itself. So we will need some way to do the sampling. We'll need some way to do the sampling. So how do we actually do the sampling? That is by using the Venn dynamics. But the Venn dynamics is eventually a kind of like a denoising process. And you will see it a little bit in just a little bit. But before that, let me put some words on the score matching. Okay, let me put a few words on the score matching. The score matching basically we're using some very fundamental calculus trick, like kind of like the something like integrate by parts things, kind of like integrate by parts things. They are very fundamental, which you are although they are working on like a double integral things, a little bit towards the advanced side, but all the tricks that is using here is by using the fundamental calculus things. Maybe I should go to here. Use a score matching. Okay, unfortunately, I didn't put the formulas right here. Okay. The formula is eventually going to be very similar to formulas of the denoise autoencoder. Let me try to find the score matching formula. Okay. Okay, so maybe I'll go back it a little bit later, but yeah, I didn't put the actual formula right there. Okay, so anyway, it is computable by using some calculus tricks 啊、所以他用了一些微积分的技巧了，基本上就让它就是像分布积分那样子啊、你可以把它微分积分哦，因为这边的 so the difficulty here is that you can see that it actually gradient to the x and what is x? X is the image itself, and you may see that our data set is in fact discrete. We only have even it is might be a really big data set, but the x is finite. The number of x is finite, so it is a discrete. So in principle, you cannot actually compute the gradient of things, but we do some integrate on this part and differential on the other part, so that we can actually do the computation. 所以它有点像是那个做分布积分嘛，一边微分一边积分。所以像这个东西把它积分起来，然后微分掉，然后它的式子就改掉。好，所以最后就会变成比较，就会像是那个 mean square error 那个样子。Okay, so this is basically you can use a score matching to get a score matching formula by using calculus to actually compute that. And then finally use the Fenian dynamics to do the sampling, kind of like this one. So this is and you can actually even at this point you can kind of forget everything about the denoising or denoising things, because the noise can pretty much does not require at this point. So right here, suppose this is a distribution. We want to, this is kind of like a distribution, and this is a gradient, the gradient of a distribution. The most density part is like this one and this one. So ideally, we'll have something like this one, and this one is a sampling process, and we'll have this guy. However, the problem is that let me check. The reason that we need to have some noise is because I'm pretty sure it has somewhere right here. Okay, this is how the Lavina dynamics right here, kind of like this one. Okay, so ideally, if we have this log gradient things, then we can use the Lamphine dynamics to approximate the distribution like this one. But the thing is, our data is very sparse. Because of the curse of dimensionality, our space is so huge. Like the case when we consider about the variational encoder, the space is so huge. So, and our data set is finite. So this turns out that we are not our data sample is more crowd or more dense to at this part. 好，所以现在我们讲的是另外一个问题，就是如果一切都是像理论上那么美好的时候，其实就解决了，你完全不需要有那些 noise 啊那些，就像刚才那样子。哦，当然我们这边还是加了一些 randomness，让它可以收敛。但是为什么 denoise 的 noise 那个很重要？这边从 score function 的角度来看的时候，你会发现一件很重要的事情。好，如果我们用 naive 的 if we use a naive score-based generative model, what would fail? What would fail? The thing is that our data is central to some density things, right here and here. So our score matching function, after we train it, it will not converge very good at the place that without data. So here is an illustration that, okay, our data is eccentric at here and here. So you will see that a lot of a part is very inaccurate. Our score function is very inaccurate at many different places. If we begin with any random point, like what we are supposed to do, because of the inaccurate part, it may not converge to what we wish it to converge to. 好，所以正常来说，它应该会收敛到这两个点上面，就不是完全收敛，但是大部分会在这个两个点的附近，这是我们可能想象中的样子。但是因为我们训练资料集中在这边和这边，中间的它的训练其实很糟糕，因为它没有资料。So because of no data available, no training data available at this sparse place, the scoring function is very inaccurate at a lot of different places. So if we run the Venn dynamics directly, because we can initial at any point, it may never reach the accurate area. So it will like circling around like here and never reach the green area. So this will make these things very difficult to actually achieve a very quality generation. So how do we solve this issue? We do this by using different level of noise perturbation. So instead of train on these really sparse things, we first make these things more. We introduce some noise in it. So that's why we need to introduce noise in. So if we introduce noise in it, the density will become a non-issue. 好，所以我们如果加上一些杂讯，我们的资料集很小，它只占整个空间的很小部分，这不好。好，那我们没关系啊，我们把这个资料集扩散，也就是说，我们加上一些杂讯。那因为加上杂讯的关系，本来你看只有小小点。So this is the original data set, kind of look like this one. If we add some noise, so the density will be more even. It will be more even. In this case, we can actually train the scoring function. I mean, according to this new perturbed density, we can train a pretty accurate scoring function. So everything should be fine. However, this is not what we wish to have. We are wishing to generate something like this one, not this one. So that's a problem. But we solve one of the problem, that is the imbalance things and inaccuracy things. So how do we start from here to there? So because this one is more like a balance, if we start from anywhere, the idea is that we start from here, we can at least getting closer. Maybe not to what we are eventually want to have, but at least unlike the case right here, they are wandering around and never go to the green area. At least in this case, although the generated quality is not good, but it is supposed to getting closer to the good area. So we train another model that is still perturbed, but not that much, and hoping that on that model, it will getting closer to the good area. And if we reduce the randomness more and more, then maybe finally we can guide the sampling process to the good areas. So that's the strategy. That's the strategy. 好，所以这就是我们的策略了。我们一开始的时候，so this is strategy. We're beginning with a very uh protruded distribution, not the ideal one, but it is more balanced, and so that we can at least guide the things a little bit, and then we try something better and guide it toward the good part even better. And finally, we have our idea distribution, and we hope it uh, should work from there. Okay, so this this story about the naive scoring matching function and this non-naive this noise condition score based model introduce the necessity of why the noise procedure is necessary. Unlike the I think unlike the story from the denoise probabilistic denoise diffusion model, it is not clearly why the denoising things is essential. But I think well it you can come up with some reasons, but like the scalability, like a lot of things. But in here, I think this is quite crucial that it demonstrated that because of our data is so imbalanced, it's so sparse. So it will make the training very inefficient. It's kind of similar to the case that for the Bayesian autoencoder. Recall that we also have a example saying that why we need to do something because we have so less sample and the space so huge. But because of those sort of kind of accuracy, this is similar. So the key point is that if we want to start from something totally random, the space is so huge and our data is so little. So by using the randomizing is necessary because there's a gap between our data to the actually true randomness initial distribution. Because they have a so huge gap, we cannot train it efficiently. Although, like in theoretically, we know that it might work if everything according to plan, if we have a perfect scoring function. But the fact is we don't have. So we will have to have something in between to guide our sampling process from a truly random initial situation to the distribution that is so different from the beginning. 好，所以这边基本上就在说明为什么那个 randomness 是有必要的，主要就是因为 data 的太过稀疏了。那我们又妄想我们又设想想要从那个全随机的地方开始，这个图都看起来都还好，但是因为真正的空间太大了，大到那个随机性太过夸张，所以他根本就没办法好好的把整个空间，你没有足够的资料去弄它，所以太多的空间其实根本盖不到。所以你为了要让整个空间都能够至少被你的训练过程，你要是完全不做事，它就是随机的嘛。你至少要做一些事情，所以让它至少能做一些事情，你就要做一些事情。那其中最简单的就是让它随机，让你的资料能够小小的影响到，有点机会影响到各个不同的地方，让你的模型能够，因为有一部分是神经网络帮你的，因为你再怎么那个做那个扩散，它其实真正的确啊，因为你最后扩散是真的很随机的，没有错。但是因为我们跑的资料太少，你真正能跑的那个数量，就算是你跑了很久很久，用很多台电脑，它的数量还是少到无法填满整个空间。所以大部分它真正能填满的是你的神经网络它的推广性。好，但不管怎样，我们做这些事情让它可以推广到所有的情况，没有那么完美，但是 现在来说至少它是可以跑的。好，所以这边的话就解释为什么那个加 noise 这件事重要的地方。Okay, this explains the necessary of why the randomness is crucial in this denoise process. Okay, so let's go back to this thing. Okay, so the first blog post also talks about the connection of noise condition score network. Also, the second blog post, which is the first one, I listed as the first one, but I took it. I mean, in the I talk it after I talk on the second one. So anyway, the thing is we can actually make a connection between this denoise process to make it more like continuous one. So instead of like 1,000 steps, why not just use it like infinite many steps? Okay, so it can actually do that to run it on infinite many steps. So it will comes to a thing called the stochastic differential equation. It turns out that the whole setting is kind of like after you add some noise things inside, it is eventually a thing called the stochastic differential equation. So because we are using a calculus, calculus is in fact making things easier. Probably kind of contrast to your experience because people already also think almost a lot of general public thinks that calculus is considered as the hard or difficult mathematics. But this is not the purpose of what the calculus is. Calculus is in fact doing things easier to be deal with. So because it is easier to deal with, so we have a lot of different tools. That's why you need to learn a lot of different things. If it is difficult, we don't even have enough tools to deal with it. Okay, so in this case, if we can continuize this, it actually makes it more elegant. So we can treat it as a stochastic differential equation. And by using differential equation, stochastic differential equation tools to solve everything, like kind of like this one. The stochastic part comes from the random part, the noise part of the things. And here it also consider the collapse in like JAX flags or in PyTorch. Maybe you should try the PyTorch part to actually it has a for explained process of the training process. So if you really want to have a deep understanding of what it is or what the diffusion model really is, this is a very good collab that you can refer to. 好，所以这边是你非常值得去看的几个 collab。如果你真的想完全了解什么是那个 diffusion model 啊，然后假设那个 SDE， 它这边比较偏向的是 SDE 的方式了。那你可以看这个。好，这边一个是那个训练过程，一个是那个做 sampling 的。主要你要看训练的这个就可以了，因为它可以从头到尾让你跑一次训练，然后你一步一步的看一下。当然，这边的前提是 ，but I mean the assumption is that you are not afraid with differential equation. You have some familiarity with differential equation. If you really hate or like I mean you have no idea what the differential equation and have no intention to understand what the differential equation and tools. Another good source to understand the actual implementation and more practical implementation is diffusers that we mentioned before, like here, the diffusers. Especially, but diffuser comes with a lot of materials. So in the next homework, in the next week, we'll have a homework to guide you through which part you should read in the diffusers example and the source code. to help you to understand, to walk through this part and I actually understand the implication of the things. Okay, before that, let's go to this broadcast and to see the next part, which is also quite important, is the conditioned generation. So people, when people see the diffusion model, the first time is probably seeing the stable diffusion. So you may think that, okay, the text prompt is an essential part of the diffusion process, diffusion model. But as you can see that we haven't mentioned anything about the text prompt or even like conditional things. So the thing is that the text prompt guided things is not the essential part of the diffusion model. They are separate. It's just a very popular flavor or ingredient in modern diffusion models. But theoretically, they are not fundamentally require each other. But still, it is quite interesting to see how does the text actually guide the image generation. And in fact, this text prompt helps a lot to the quality of the modern diffusion models, especially for the early stable diffusion, like stable diffusion 1.3 and 1.4, exactly. They are one of the common prompt guided method is called the classify free guidance. You will see like a CFG, which stands for classify free guidance, which we will introduce after the classify guided diffusion. So how do we actually add condition into the generation? One way to do that is pretty easy. Is that no matter how you do that, like you see that the model here, we only take like the xt right here, right? And the t right here. So we can actually add one more parameter to the model. And this can be a condition. So that's one way to do that. And the easy way to actually inject the condition into the model. And the people still do that. But the thing is, how do we actually define the loss function? And how do we actually do that in the sampling? Can we do that after we do the training to actually kind of like a plug-in to do so? Also, that's a lot of different consideration. But fundamentally, just like other neural network model, if you want to inject information into the model or condition into a model, one simplest way to do that is just to, okay, kind of extend your model to do whatever you want. There are many different ways to do that, to actually let the condition to go inside into to take the condition as one of the input, additional input for the model. 所以最简单的话，当然就是你这个模型再增加一个新的输入，然后你的文字啊，反正你爱怎么压就怎么压，你就用 clip 啊，用什么模型，你就随便把那个文字把它压成一个向量，然后输到这个模型里头。反正你都这边可以加了一个时间的嘛，你就用其他方法加也可以啊。但是你还是需要一些像是 loss function 啊那些东西。Okay, so one way to do that is to do the classifier guided diffusion. So that is introduced in this paper. So how does it does? It the idea is that it introduced another thing called a classifier. So it is a separate model. this classifier provide additional information to alter to alert to alter the probability distribution. So after when we do the sampling, we are manipulating the sampling distribution, right? So we are one way to do that is to consider, okay, so suppose we have a classifier. So if we consider the classifier's output, so we can change the distribution a little bit according to the classifier's output. So that's the way the classifier guided diffusion model to do that. In this case, it mostly considering the categorical class, like in MNIST, we have 0, 1, 2, 3, 4, 5 different digits, or maybe like in ImageNet, we have a different kind of animal. So it is mostly consider that kind of sense. But this one also works for like text sense, but it needs some modifications. So this one is called the classifier guided diffusion. It almost always comes with the conditional input, like I mentioned before. Just it add more things like classifier on the sampling time. It do some modifications. It also do things like there. So it by altering the noise prediction primarily, but it alone does not work very well. So it always kind of combine with the things we see before. So here is the algorithm. I didn't go to too much detail about it. I'm just mentioned that there is a classifier guided method. The only thing you need to worry about or need to the main notice about is that this classifier, although you can add it after the training. So one thing is that you probably still need a conditional input thing combine with it to have a better performance. The other thing is this classifier, you will probably need some spatial design classifier so that this classifier works with a noisy image, because you can see that this is classifier, and this classifier need the noisy image as input. So it pretty much means that you cannot just take any classifier off the shelf and use on a classifier guided diffusion sampling, because it may not work, because they may not work well on a image with a lot of noise. You probably will kind of fine tuning or retraining it on a noise image. That's it, before you can actually use it to guide the diffusion model. But anyway, this is one approach that people use. Although I don't think it is that popular, but I mean, yeah, it is something that in your toolbox you can use. 所以这个现在比较少用了。其实它因为它比较难用一点点，因为它的 classifier 那个需要特别设计，它不能用，它需要，因为你看它吃的东西是有杂讯的影片嘛，有杂讯的图片，所以你的那个 classifier 不是你随便路上随便什么 ImageNet 啊什么东西随便找一个就行了，它需要能够吃有杂讯的图片，而且它单拿来用的时候效果通常不会很好。虽然它这边的那个 formulation 就是看起来就单拿来用是没有错了，然后你可以事后再拿来用也都可以，看起来是这样，但实际上用起来效果没有很好所以一般来说都会再配合那个，就它原版也是这样做，会配合一个 conditional input， 就像我刚才讲的，这边看不出来，但是实际上它会再配合一个，通常都会有一个 conditional input， 会让它效果再好一点点。所以现在比较少用，所以我没有讲很详细。但是你以后反正这是一个可以用的工具啊。 那它也不是只有用 category，它用那个文字也可以，就是你把那个这个换成 clip，用相同的原理去做，可以做类似的事情。Okay, however, the more popular one is the classifier free guidance. Like I said, you will see like a CFG in like Comfy UI or in other models like a CFG. It's always referred to the classifier free guidance method. So this one, it does not require an independent classifier. However, this one is more like you need to do it when you do the training altogether. Uh, just but people use it a lot, so it is kind of embedded or like integrated into almost every new uh, or existing or popular diffusion model systems. You don't need to worry too much about it, but it is in the architecture. It is not a plugin. It is not a plugin. So if you have a given diffusion model, if it doesn't come with a conditional thing, which I don't think you will find too much about it. But if it does not come with anything, like a text prompt condition or other condition, you want to add some condition, you probably will like to fine tuning or kind of to modify the architecture and to do the training altogether, something like in order to get a classifier free guidance. You need to do some operations instead of just, in theory, the classifier guidance diffusion, you can actually do it in the prediction time, to do it in the inference time. You can do that. Though, because of the quality, people are using classifier free guidance. It has much better quality. So in this case, it is also as a conditional model like this one, you can see right here. 主要就是在这边你可以看到，就它很干脆的就。The key point is that it allows that you have an empty condition, so that you can mix up with the training with conditional generation and unconditional generation altogether. 好，所以它的重点是它这是一个还不错的程序了。你的资料里头有的时候它会有 condition 嘛，就是文字啊那些东西，有的时候没有嘛。然后它就很单纯的就是好，你没有文字还没关系，你就给个空的。所以你可以完全都是两个都去，就是有 condition 没 condition 都可以来做。And the inference process or the actual process is combined with these two things altogether, the conditional things and the unconditional things altogether. Okay, so the final, this is also the CFG parameter, like you will see like the CFG parameter like is right here. So we actually have two, when you do a sampling, you actually have two denoise model. One is a conditional denoise model, and the other is unconditional denoise model. They are the same, just one with empty condition and one with condition. And when you have these two models all together, instead of using them separately, we are combining them together using W plus 1 times the conditional one minus the W unconditional one. This one will be replaced effectively as your denoise model. This one is the final model that you're going to use when you do the sampling. 好，所以在 sampling 的时候，这个东西就是你把这两个东西合在一起，就是你要的东西了。这是你要的东西，然后就带入原来的式子。So you plug in this one into the original sampling process, no matter what sampling process you are using. and this one is going to follow the promise, follow your condition. Okay, so this classify free guidance also can be used for like a categorical or other things, but like you will see that in like stable diffusion, flux, okay, and other models, they are using similar method, and you will see like the CFG parameter is the same factor you are seeing here. So this one is not a factor that you can like a 7 or like 12 like CFG parameters, CFG scale. Okay, so this is the classifier free guidance method that you use a lot for like stable diffusion and flux. Okay, so how does what is in fact the stable diffusion model? How does it work and how does it differ from other diffusion model? Okay, so let's check the stable a brief history of stable diffusion model. The original similar one from the history view, a paper is called the Transformer Text Model and Image Generation. It's a kind of like the VQVAE, like a VQVAE, but instead of using like the pixel CNN, they are using a transformer to generate the latent. So this guy is called a VQVAE. But you can see that at the beginning, we have a encoder, a VQ encoder, and a VQ decoder. Okay. So this one can take the text prompt very straightforward because we have a transformer right here. 好，所以这是我们一开始先有 VQ gain，那 VQ gain 它前面有一个那个 latent 啊那些东西 encoder 啊 decoder 啊这些东西，它有它的训练方式，然后那些东西都差不多都长得那样子，然后它其实它的那个 encoder decoder 都已经做得非常好了。And basically, the stable diffusion takes the encoder and the decoder from VQ gain, but they are not using the Q part. They are using just the encoder and the decoder part. So that they are working on the latent space instead of working on the they are just working on the latent space instead of working on the pixel space. That's it. Okay, so because we already have a certain like encoder and the decoder and pretty good encoder and decoder, so the latent diffusion take advantage of this one. So they are using instead because diffusion model works very computational extensive, and they didn't work very well on a very high resolution things. So instead of working on a very, I mean, at the beginning, they didn't work very well on a very high resolution setting. They are working pretty well on maybe up to 128 to 128, sometimes to like 225, 225, 250 by 250. But if you are going up to like 500 by 500, it has already been considered very high resolution at the big when we at the beginning when the diffusion model getting success. They work pretty good on medium to low resolution things. So to work around with this limitation, latent diffusion introduced a very straightforward way to actually reduce the dimension to lower dimension latent space. I mean, the image itself may have a higher dimension, like 500 by 500 or like 1K, like 1000 by 1000. They will have this high resolution. Currently, maybe you can generate like 4K or even 8K or even video. But back then, it is very difficult to do so. So instead of generate a high resolution image directly, people try different methods to do that, like using hierarchy way, like generate low resolution, then do super resolution. Or this is like a Google method, or like DALI. Maybe they use similar method, but the stable diffusion using latent space instead. So instead of generate a low resolution image, it generates in latent space. But latent space is comparable the low resolution compared to the high resolution space. I mean the image pixel space. So it will have like a 4 channel or maybe up to 16 channel, but they don't have much channel. The 4 channel sense is similar to or low channel sense is inherent from like a video game. But in other settings, then people exploring with different number of dimension of the channel of latent space. But in latent diffusion or stable diffusion, they are using things like 4 channel and low resolution setting. Okay, so after you get into the you use the encoder to, I mean, when you're training, when you do the training, you need to have image from data set, and you use the encoder to encoding the image into latent space and to do your thing. But when you do the decoding, I mean, to do the generation, encoder does not necessary. You just use the decoder. I mean, you start from the latent space, and then you generate the final latent, and you use the decoder to decode the latent into an image. So that is probably the process. But after you go into the latent space, what does the diffusion model do? What does the stable diffusion or latent diffusion model do? The latent diffusion, this is the architecture of the latent diffusion. And the stable diffusion pretty much remains the same. It uses a denoising U-net. So what is a denoising U-net? It is pretty much similar to a U-net. Instead, they have like attention blocks between the connection between the layers. So they connect them by attention layer. So that we call it the attention unit. It is not the original unit, but the attentional unit. So we'll have the original latent diffusion or stable diffusion. They are using attention unit as the denoising network. Denoising network. Okay, so it contains like the autoencoder here and the denoising unit right here. And I think latent diffusion also use the classifier guided method. So the only difference that noticeable, aside from, I mean, more training data, different training data, different training setting, or like the different hyperparameters things, the major difference is that a stable diffusion uses classifier free guidance, and the latent diffusion, I believe, is still using the classifier guidance method. So that's the only difference. But this is pretty much the architecture of the stable diffusion, and the stable diffusion also using the classifier free guidance。好，所以基本上 latent diffusion 跟 stable diffusion 差不多就已经是一模一样，它们的参数啊可能有些差异性啊，那些东西有点差异性，但是最主要差异其实是他们 guidance 的部分哦，它有用那个classifier free guidance 跟那个 classifier guidance 啊，主要就差在这边了，他们主要其实就差在这个地方。好，那所以 stable diffusion 原则上就是 latent diffusion 加上那个 classifier free guidance， 特别是早期，主要是我现在讲的主要是早期的 1.5 之前的在 1.5 之前的的东西 1.3 啊 1.4 啊 1.2 1.3 1.4， 他们中间后来又分家或干什么的但是早期的话，他们的模型基本上这个就是 stable diffusion 它本身的架构。OK， So we in this week we get a very quick overview, walkthrough of what the diffusion model is, the basic idea and the foundation of it, and why it works. And at the end, we introduce the stable diffusion, latent diffusion, and stable diffusion. Basically, stable diffusion and latent diffusion. I mean, latent diffusion is simply working on a diffusion model working on the latent space. And the use of like the attention unit is kind of standard. And I mean, in the early time they explored a lot, but I think in the diffusion model bit can already use modern architecture like attention unit already. So this is not so surprising. But I mean, apparently the latent diffusion already is also using the attention unit, and the stable diffusion up to like 1.5. They are fundamentally they are just they are basically just the latent diffusion, but they are using classified free guidance, and they are using CLIP. Also, they are using CLIP model to do the text encoding for their text-free guidance. Okay. Next week we are going to give you a homework to read through and run through some code and examples of the diffusion models in diffusers. So you will actually notice everything we talk about today and in the code. And right now, the diffusion model we are introducing so far is probably most of them are before like 2022 or 2023, maybe 2023, but not later. There are a lot of new advances in diffusion models, like consistent model, and a lot of different improvement on the models. So that's what we are going to talk about next week. We are going to talk more about the advance of the diffusion models. Okay, so that's all for today.